Learn like a pro.
Welcome to The Explainer. Today we're diving into something that seems, well, like a paradox. We're going to look at how the completely random, unpredictable decay of a single atom can somehow turn into one of the most reliable clocks in the entire universe. So yeah, that's the big question, isn't it? It just doesn't seem like it should work. How can something that's pure chance, completely unpredictable at its core, also be as regular and precise as a ticking clock? Okay, to get our heads around this, we have to shrink way, way down to a scale that's almost impossible to imagine. We're talking about the inside of one single unstable atomic nucleus. The best way to think about it? It's like an atomic lottery. So picture just one of these unstable nuclei sitting there. The question is, when is it going to decay? And the honest answer is, we have absolutely no clue. It could pop right this second, or it could sit there for a million years. It is pure 100% chance. Okay, but here's the twist. While that one single atom is a total mystery, what happens when you get a whole bunch of them together? Well, a huge group of them behaves in a way that is incredibly predictable. The lottery analogy is perfect, right? You have no way of knowing if your ticket is the winner, but the Lottery Commission knows with statistical certainty that if they sell millions of tickets, someone is going to win. So that's the puzzle we're trying to solve. How do we take all that quantum-level chaos, that big atomic lottery, and actually turn it into a tool, something so reliable that we can literally use it as a clock to measure time? Well, the secret, it turns out, is all about perspective. We need to stop focusing on that one single unpredictable atom, and instead, zoom out, way out. Let's watch trillions of them all at the same time. And this is where the magic really starts to happen. And boom, there it is. You can see it right here. All those little random pops from individual atoms, they start to average out. And what you get is this perfectly smooth, totally predictable curve. The chaos from the tiny micro world just smooths itself out into perfect, beautiful order when you look at the big picture.
Now, this predictable curve is governed by one really important idea. It's called half-life. And all it means is the amount of time it takes for exactly half of the unstable atoms in a sample to decay. The amazing thing is, for any specific radioactive element, that half-life is a constant. It never, ever changes.
And this halving principle just keeps on going, like clockwork. You wait one half-life, and boom, half the radioactive stuff is gone. You wait another half-life, and half of what was left is gone. A quarter of the original is now left. And it just keeps going. It doesn't matter if you start with a handful of atoms or a mountain of them. The pattern is always the same. Half, then half again, relentlessly. Okay, so it sounds pretty straightforward, right? But of course, there's a catch. In the real world, it's not that simple. Our detectors, the things we use to measure this decay, are always picking up this low-level hum of radiation from, well, everywhere. It's like trying to listen to a tiny whisper in the middle of a really noisy room. This universal noise is what we call background radiation. And it really does come from everything. The rocks in the ground, cosmic rays zipping in from deep space, even things we do, like getting a medical X-ray. It's this constant background chatter that we have to figure out how to ignore. So how do scientists deal with it? The solution is actually pretty clever and surprisingly simple. What they do is, they first measure just the background noise by itself. They use a detector like a Geiger counter with no sample nearby. They figure out what that constant hum is, and then they just subtract it from whatever reading they get when they do measure their sample. Easy. And you can actually see the proof of this right here on the graph. As our sample decays, its signal gets weaker and weaker until eventually the curve just flattens out completely. That flat part at the end, that is the background noise. It's the background floor of radiation that's always there, perfectly revealed once our sample signal has faded away. Okay, so let's put all these pieces together. We know about half-life, and we know how to correct for background noise. With this toolkit, we can actually start to make some incredibly accurate predictions. Let's try a real-world example. Say we've got a sample of a nitrogen isotope. We measure its activity right now, and it's at 16,000 counts per second. We also know its half-life is exactly 7 seconds. So the question is, what's the count rate going to be after 42 seconds have passed? All right, the math here is actually pretty simple. First step, how many half-lives are in 42 seconds? Well, 42 divided by 7 is 6. So we're going through exactly 6 half-life cycles.
That means all we have to do is take our starting number, 16,000, and cut it in half 6 times. So 16,000 becomes 8,000, then 4,000, 2,000, 1,000, 500, and finally, after 6 steps, we land on our answer, 250 counts per second. See? Perfectly predictable.
So, this brings us right back to where we started, back to that big paradox. This idea that a single atom is totally random, but a huge group of them is the exact opposite. And this right here is the answer. It's so cool, the randomness at the quantum level doesn't actually create chaos in the big picture. Instead, something called the law of large numbers takes over. It transforms all that individual randomness into a statistical certainty, a certainty so powerful and so reliable that it literally becomes a rock-solid clock we can use.
You know, this whole principle isn't just a neat science trick. It's the foundation for so much, from figuring out how old ancient fossils are with carbon dating to the medical imaging we use in hospitals today. It's this incredible clock that's literally built into the fabric of our universe. Which kind of leaves you wondering, right? What other secrets of the past, or the future, can it help us unlock?